Let's take a look at another example of hypothesis testing. Coca-Cola tested their machines that fill their 12-ounce cans of soda. After collecting 1,300 samples of regular Coke, they found the average amount of soda in a can of regular Coke is 11.945 ounces, with a standard deviation of 0.03 ounces. After collecting 1,500 samples of Coke Zero, they found the average amount of soda in a can of Coke Zero is 11.94 ounces with a standard deviation of 0.035 ounces. At alpha equals 0.05, can it be concluded the average amount of soda in a Coke Zero is less than that of regular Coke? Compute Cohen's d, describe the relationship between both Cohen's d and the result of the hypothesis testing for this example. Okay, so the first thing we have to do is we have to look at the statistical side of this. We're doing hypothesis testing with alpha equals 0.05 or a significance level of 5%. So we'll introduce some of our subscripts here. So we'll say mu sub r is going to be the mean of regular Coke. And then we'll say mu sub z will be the mean of Coke Zero. So my null hypothesis says that these two are the same, that we have just the same average amount in both regular Coke as well as Coke Zero. But the alternative hypothesis is now testing, is there actually more that's in the regular? Or in other words, is there less in Coke Zero? So now when we do the All right. So now when we decide on our test here, our few comments here we have is we have two sample tests. We have looking at means. We have unknown population standard deviations, because we see that we're talking about the samples that have standard deviations, and then we have a one-tailed test. Looking at these first three, we see that we're going to be looking at a two-sample t-test. So if we go to our calculator, we'll go to stat, we'll go over to tests, we'll go down to two-sample t-tests. We have our stats. We can type them in. X1 is 11.4945. The sample standard deviation is 0.03, and enter in all of this lovely information from the calculator, or from the question. Our alternative hypothesis, we're looking for mu sub 1 is larger than mu sub 2. And then we never pool, and we calculate this. What we see is we now have a test statistic that is t is equal to 4.398. Very, very large test statistic. So our p-value we expect to be very small, and it is indeed 0.0000566. Now also, if you notice on the calculator, on the third or the fourth row, it says DF. This is our degrees of freedom. So the distribution that we're really working with is a T sub 2741.72. So this is this number right here. This is our degrees of freedom. Because remember, we saw that the formula that we had was a real nasty formula. So the calculator just does that for us. So now that we are at the test statistics and p-value point, now we can finish off our hypothesis testing. So what we can say now is that since the p-value, which is equal to 0.0000566, is less than 0.05, which is the alpha value, we reject the null hypothesis. There is sufficient evidence to believe Coke Zero has less in the can than regular Coke. Okay, so that is what our statistical result says. Now if we carry on to looking at Cohen's D, so if we have Cohen's D, we had the formula that we used in the previous video. I won't rewrite that. I will just plug in the numbers at this point. So we have 11.945 minus 11.94 divided by a square root of 1299 times 0.03 squared plus 1499 times 0.035 squared. All of this is now divided by 2,798. And again, you can throw in absolute values just to make sure you have a positive answer, or just make sure your answer is always positive. We get 0.15. So if we remember the cutoffs, the small cutoff was 0.2. So this we see is that there is a very small effect size. So what this is saying now is that if there's a very small effect size, this says that there is a very small practical difference. So notice over here, we said that there is a statistical difference. Our p-value was extremely small. So statistically speaking, the two numbers that we had were very different. So having in this case, the mean of 11.945 versus a mean of 11.94, because our samples were gigantic, we had 1,300 and then we had 1,500, these two are statistically different numbers. The means were different. But that's where the practical significance can come in and say, well, practically though, that's a very small difference. There's not really that much of a difference between 11.945 and 11.94. So we have a very small practical difference. So this is one of those situations where if you are making decisions as in charge of a Coca-Cola manufacturing, yes, statistically there's a difference, but will people really know that there is less Coke Zero in the can than regular Coke? No. So if it costs a lot of money to make fixes, you probably won't buy new machinery and make the fixes. So indeed, this is the types of situations that Cohen's D can be very helpful in figuring out the difference between statistical significance and practical significance.